40 Most Amazing Things Seen by Chandra X-ray Observatory. Hello everyone, welcome to Space Explorer channel. In the vast expanse of the universe, hidden from the naked eye, lies a treasure trove of celestial wonders waiting to be discovered. Among the tools of exploration, the Chandra X-ray Observatory stands as a beacon of scientific ingenuity, revealing the universe in a new light. Launched by NASA in 1999, Chandra has been peering into the depths of space with its X-ray vision, uncovering phenomena that challenge our understanding of the cosmos. From distant galaxies to enigmatic black holes, Chandra has provided astronomers with a wealth of groundbreaking discoveries. In this article, we embark on a journey through 40 of the most remarkable sights witnessed by the Chandra X-ray Observatory, each one illuminating the mysteries of the universe in its own unique way. Before moving forward, if you are new to our channel, please don't forget to like and subscribe our channel for future interesting videos. 1. Black hole feeding frenzy. Chandra's observations of black hole feeding frenzies have revealed the existence of supermassive black holes at the centers of galaxies, with masses millions to billions of times that of the Sun. These black holes attract surrounding gas and stars due to their immense gravitational pull. As matter spirals inward towards the black hole, it forms an accretion disk, swirling disk of hot gas and dust orbiting around the black hole. Friction within the accretion disk heats the gas to temperatures of millions of degrees, causing it to emit X-rays. 2. Cosmic cannibalism. Galactic collisions and mergers are common occurrences in the universe, driven by the mutual gravitational attraction between galaxies within galaxy clusters. When galaxies collide, their stars, gas, and dust interact gravitationally, leading to dramatic transformations in their shapes and structures. During these collisions, massive black holes at the centers of galaxies can also merge, resulting in the formation of an even larger black hole. 3. Supernova remnants. Supernova remnants are the expanding shells of gas and dust left behind by the explosive deaths of massive stars. When a massive star reaches the end of its life, it undergoes a cataclysmic explosion known as a supernova, which can briefly outshine entire galaxies. The explosion ejects the star's outer layers into space at velocities of thousands of kilometers per second, generating shock waves that heat the surrounding interstellar medium. 4. Neutron stars. Neutron stars are the ultra-dense remnants of massive stars that have exhausted their nuclear fuel and undergone gravitational collapse. With masses up to twice that of the Sun, compressed into a sphere just a few kilometers in diameter, neutron stars are among the densest objects in the universe. Chandra's detection of X-ray emissions from neutron stars reveals their extreme physical conditions, including intense magnetic fields, rapid rotation, and powerful gravitational fields. 5. Pulsar wind nebulae. Pulsar wind nebulae are luminous structures powered by the intense radiation and high-speed particles emitted by pulsars, rapidly rotating neutron stars with powerful magnetic fields. As the pulsar spins, it generates a wind of energetic particles that streams outward into space, interacting with the surrounding interstellar medium. Chandra's observations of pulsar wind nebulae reveal the complex dynamics of particle acceleration, magnetic fields, and shock waves within these nebulae. 6. Dark matter maps. Dark matter is a mysterious form of matter that does not emit, absorb, or reflect electromagnetic radiation, making it invisible to traditional telescopes. However, its presence can be inferred from its gravitational effects on visible matter, such as stars and galaxies. Chandra's observations of galaxy clusters provide indirect evidence for the existence of dark matter through the study of the intracluster medium, ICM, hot, X-ray emitting gas that fills the space between galaxies and clusters. 7. Black hole jets. Black hole jets are powerful streams of particles and radiation emitted from the vicinity of supermassive black holes at the centers of galaxies. These jets can extend for millions of light years into space, impacting their surrounding environments and influencing the evolution of galaxies. Chandra's images of black hole jets reveal the mechanisms responsible for launching and collimating these jets, including magnetic fields, accretion disks, and relativistic plasma. 8. Galaxy clusters. Galaxy clusters are the largest gravitationally bound structures in the universe, consisting of hundreds to thousands of galaxies bound together by gravity. The vast majority of the cluster's mass is in the form of dark matter, which emits no light but can be detected through its gravitational effects on visible matter. Chandra's observations of galaxy clusters reveal the presence of hot, X-ray emitting gas known as the intracluster medium, ICM, which fills the space between galaxies. 9. Quasar outflows. Quasars are the most luminous and energetic objects in the universe, powered by the accretion of matter onto supermassive black holes at the centers of galaxies. As matter spirals into the black hole's accretion disk, it releases a tremendous amount of energy in the form of radiation and powerful outflows of gas. Chandra's observations of quasar outflows reveal the impact of these energetic jets on the surrounding interstellar medium and host galaxies. These outflows can drive shock waves, heat the surrounding gas, and regulate star formation, influencing the growth and evolution of galaxies over cosmic timescales. 10. Galactic winds. Galactic winds are powerful streams of gas ejected from galaxies, driven by processes such as supernova explosions, stellar winds, and the activity of supermassive black holes. These winds can carry significant amounts of gas and dust out of galaxies into the surrounding intergalactic medium, enriching it with heavy elements synthesized in stars. Chandra's observations of galactic winds reveal the complex interplay between stellar feedback, gas dynamics, and the gravitational potential of galaxies. 11. X-ray binaries. X-ray binaries are binary star systems in which one of the stars is a compact object such as a neutron star or black hole accreting matter from its companion star. As matter from the companion star spirals inward towards the compact object, it forms an accretion disk that emits X-rays due to the high temperatures and velocities involved. Chandra's detection of X-ray emissions from binary star systems provides insights into the physical processes of accretion, mass transfer, and energy release in these systems. X-ray binaries exhibit a variety of phenomena, including periodic X-ray pulsations, bursts, and flares, which astronomers use to study the properties of compact objects and their binary companions. 12. Exoplanet transits. Exoplanet transits occur when a planet passes in front of its host star, causing a slight decrease in the star's brightness as seen from Earth. Chandra's monitoring of X-ray emissions from stars during exoplanet transits offers a unique opportunity to study the properties of planetary atmospheres. As the planet crosses in front of the star, it blocks a fraction of the X-ray emissions originating from the star's corona, a region of hot, magnetically active gas surrounding the star. 13. X-ray auroras. X-ray auroras are phenomena observed on planets with magnetic fields, such as Earth and Jupiter, where charged particles from the solar wind interact with the planet's magnetic field and atmosphere. These interactions result in the emission of X-rays from regions near the planet's magnetic poles, analogous to the auroras seen at Earth's poles. Chandra's observations of X-ray auroras on Jupiter and other planets provide insights into the complex interplay between planetary magnetic fields, solar wind particles, and atmospheric gases. 14. Magnetars. Magnetars are a rare class of neutron stars with ultra-strong magnetic fields, up to 1,000 times stronger than typical neutron stars. These intense magnetic fields give rise to exotic phenomena, including sporadic bursts of X-ray and gamma-ray emission, which can outshine entire galaxies for brief periods of time. Chandra's detection of magnetars provides insights into their extreme physical conditions and the mechanisms responsible for their explosive behavior. Magnetars are thought to be the remnants of massive stars that undergo supernova explosions, leaving behind highly magnetized cores that exhibit rapid rotation and intense magnetic activity. 15. Gamma ray bursts. Gamma ray bursts, GRBs, are the most energetic explosions in the universe, releasing as much energy in a few seconds as the sun will emit over its entire lifetime. These brief but intense flashes of gamma ray radiation are thought to result from catastrophic events such as the collapse of massive stars or the merger of binary neutron stars. Chandra's rapid response to GRB alerts allows astronomers to study the X-ray afterglows of these events, which can persist for days to weeks after the initial gamma ray burst. 16. Galactic nuclei. Galactic nuclei are the central regions of galaxies, where supermassive black holes reside and exert a profound influence on their host galaxies. Chandra's deep surveys of galactic nuclei reveal a diverse population of black holes, ranging from quiescent to actively accreting objects. Active galactic nuclei, AGNs, are powered by the accretion of matter onto supermassive black holes, which emits intense radiation across the electromagnetic spectrum, including X-rays. Chandra's observations of AGNs provide insights into the growth history, feeding mechanisms, and feedback effects of black holes on their host galaxies, shedding light on the coevolution of galaxies and their central black holes. 17. Stellar coronas. Stellar coronas are regions of hot, magnetically active gas surrounding stars, including our Sun. These coronae are heated to temperatures of millions of degrees by magnetic reconnection events and other processes driven by the star's magnetic field. Chandra's observations of stellar coronae reveal the complex interplay between magnetic fields, plasma dynamics, and energy release mechanisms within these regions. Stellar coronae emit X-rays due to the heating and acceleration of charged particles in magnetic loops and flares, providing valuable insights into stellar activity cycles, magnetic field structures, and the physics of stellar atmospheres. 18. Galactic bulges. Galactic bulges are centrally concentrated regions of stars and gas found at the centers of spiral and elliptical galaxies. These bulges contain dense stellar populations, including old stars and massive star clusters, as well as supermassive black holes at their cores. Chandra's high-resolution imaging of galactic bulges reveals the presence of X-ray emitting sources, including accreting black holes, X-ray binaries, and hot gas. These X-ray emissions provide insights into the physical processes occurring within galactic bulges, such as star formation, black hole accretion, and the dynamics of stellar populations. 19. Accretion disks. Accretion disks are flattened structures of gas and dust that form around compact objects such as black holes, neutron stars, and white dwarfs as they accrete matter from their surroundings. These disks emit radiation across the electromagnetic spectrum, with X-rays being particularly prominent due to the high temperatures and densities of the inner regions of the disk. Chandra's observations of accretion disks reveal the dynamics of matter as it spirals inward towards the central object, generating intense X-ray emissions. 20. High-energy particle acceleration. High-energy particle acceleration is a fundamental process occurring in various astrophysical environments, including supernova remnants, active galactic nuclei, and galaxy clusters. These environments contain powerful shock waves, magnetic fields, and electric fields capable of accelerating charged particles to speeds approaching the speed of light. Chandra's detection of high-energy particles, such as cosmic rays and relativistic electrons, provides insights into the mechanisms responsible for particle acceleration and the sources of high-energy radiation in the universe. 21. Intergalactic gas filaments. Intergalactic gas filaments are the largest known structures in the universe, spanning hundreds of millions of light years and connecting galaxies across cosmic distances. These filaments consist of diffuse gas, primarily hydrogen and helium, heated to temperatures of millions of degrees by gravitational collapse and cosmic shocks. Chandra's observations of intergalactic gas filaments reveal the presence of X-ray emitting gas, providing insights into the large-scale structure of the universe and the distribution of baryonic matter. 22. Galactic halos. Galactic halos are extended regions of gas and dark matter surrounding galaxies, extending far beyond their visible boundaries. These halos contain hot, X-ray emitting gas enriched with heavy elements synthesized in stars and supernovae, as well as dark matter, which dominates the gravitational mass of the halo. Chandra's studies of galactic halos reveal the complex interplay between stellar feedback, gas dynamics, and the gravitational potential of galaxies. 23. Starburst galaxies. Starburst galaxies are galaxies undergoing intense episodes of star formation, producing stars at rates hundreds to thousands of times greater than in typical galaxies. These bursts of star formation are often triggered by galaxy collisions, mergers, or interactions with neighboring galaxies, which compress gas and dust in the galaxy's disk and trigger the formation of massive star clusters. Chandra's X-ray observations of starburst galaxies reveal the presence of hot, X-ray emitting gas associated with regions of intense star formation. These X-ray emissions are produced by supernova explosions, stellar winds, and accretion onto black holes, providing insights into the feedback processes regulating star formation and galactic evolution. 24. Ultra-compact dwarf galaxies. Ultra-compact dwarf galaxies are small, dense galaxies found in the outskirts of galaxy clusters, with masses ranging from a few million to a few billion times that of the Sun. These galaxies contain old stellar populations and little gas, making them challenging to detect and study using traditional observational techniques. Chandra's detection of X-ray emissions from ultra-compact dwarf galaxies reveals the presence of hot, X-ray emitting gas associated with stellar processes such as supernova explosions and X-ray binaries. 25. Tidal disruption events. Tidal disruption events occur when a star passes too close to a supermassive black hole at the center of a galaxy, leading to its tidal disruption and subsequent accretion onto the black hole. During this process, the star is stretched and torn apart by the immense gravitational forces of the black hole, generating a brief but intense flare of radiation across the electromagnetic spectrum. Chandra's observations of tidal disruption events reveal the presence of hot, X-ray emitting gas produced by the accretion of stellar debris onto the black hole's accretion disk. 26. Intracluster medium. The intracluster medium, ICM, is the hot, X-ray emitting gas that fills the space between galaxies and galaxy clusters, constituting the largest baryonic reservoir in the universe. The ICM is heated to temperatures of tens to hundreds of millions of degrees by gravitational collapse and shocks associated with the formation of galaxy clusters. Chandra's observations of the ICM reveal the complex dynamics of gas heating, cooling, and turbulence within clusters, as well as the interactions between the ICM and individual galaxies. 27. Cosmic microwave background. The cosmic microwave background, CMB, is the relic radiation left over from the hot, dense phase of the early universe, emitted approximately 380,000 years after the Big Bang. The CMB pervades the entire universe and provides a snapshot of the universe's state at that time, containing valuable information about its composition, geometry, and evolution. Chandra's observations of galaxy clusters contribute to our understanding of the CMB through the Sunyaev-Zeldovich effect, the distortion of CMB photons as they pass through hot cluster gas. 28. Magnetohydrodynamic turbulence. Magnetohydrodynamic, MHD, turbulence is a fundamental process occurring in magnetized plasmas, such as those found in galaxy clusters, supernova remnants, and accretion disks. MHD turbulence arises from the interactions between magnetic fields and fluid motions, leading to the generation of eddies, shocks, and fluctuations in plasma density and temperature. Chandra's studies of galaxy clusters reveal the presence of MHD turbulence in the intracluster medium, ICM, driven by processes such as galaxy mergers, accretion shocks, and feedback from active galactic nuclei. 29. Gravitational lensing. Gravitational lensing is a phenomenon predicted by Einstein's theory of general relativity, in which the gravitational field of a massive object bends and distorts the paths of light rays passing nearby. This effect can magnify, distort, or even multiply the images of background objects, such as galaxies and quasars, as seen from Earth. Chandra's observations of gravitational lensing by galaxy clusters enable astronomers to study the distribution of dark matter and the properties of distant galaxies. 30. Stellar explosions. Stellar explosions are cataclysmic events that mark the deaths of massive stars, including supernovae, gamma-ray bursts, and kilonova. These explosions release vast amounts of energy and synthesize heavy elements, enriching the interstellar medium with elements essential for the formation of new stars and planets. Chandra's monitoring of stellar explosions provides insights into the physics of supernova remnants, the properties of gamma-ray burst afterglows, and the nucleosynthesis processes occurring in these environments. 31. Interstellar medium. The interstellar medium, ISM, is the gas and dust that fills the space between stars and galaxies, providing the raw material for star formation and the recycling of stellar material. The ISM consists primarily of hydrogen and helium, as well as trace amounts of heavier elements synthesized in stars and supernovae. Chandra's observations of the interstellar medium reveal the presence of hot, X-ray emitting gas associated with regions of recent star formation, supernova remnants, and galactic outflows. 32. X-ray binary populations. X-ray binaries are binary star systems in which one of the stars is a compact object such as a neutron star or black hole accreting matter from its companion star. Chandra's surveys of X-ray binaries in nearby galaxies reveal the demographics and evolutionary pathways of these systems, providing insights into the physics of mass transfer, accretion, and binary interactions. X-ray binaries exhibit a wide range of properties, including periodic X-ray pulsations, bursts, and variability, which astronomers use to classify and study different types of binaries. 33. Galactic feedback. Galactic feedback is the process by which galaxies regulate their star formation rates and gas content through the injection of energy, momentum, and heavy elements into their surroundings. This feedback can be driven by supernovae, stellar winds, black hole accretion, and other astrophysical processes, which heat, ionize, and expel gas from galaxies into the intergalactic medium. Chandra's observations of galactic feedback processes provide insights into the mechanisms regulating star formation, gas dynamics, and the chemical enrichment of galactic environments. 34. Dwarf galaxy evolution. Dwarf galaxies are small, low-mass galaxies found throughout the universe, ranging from faint dwarf spheroidal galaxies to gas-rich dwarf irregular galaxies. These galaxies are thought to be building blocks of larger galaxies and are susceptible to environmental influences such as tidal interactions, gas stripping, and galaxy harassment in dense environments. Chandra's studies of dwarf galaxies reveal the impact of these environmental factors on their star formation histories, morphologies, and X-ray properties. 35. X-ray emitting supernovae. X-ray emitting supernovae are stellar explosions that release vast amounts of energy and synthesize heavy elements, enriching the interstellar medium with elements essential for the formation of new stars and planets. Chandra's detection of X-ray emissions from supernovae provides insights into the late-stage evolution of massive stars and the dynamics of their explosive deaths. X-ray emissions from supernovae arise from shock heating and particle acceleration in supernova remnants, producing intense radiation across the electromagnetic spectrum. 36. Extragalactic background light. The extragalactic background light, EBO, is the cumulative emission from stars and galaxies throughout cosmic history, stretching from ultraviolet to infrared wavelengths. The EBO contains valuable information about the history of star formation, galaxy evolution, and the buildup of cosmic structures over billions of years. Chandra's deep surveys contribute to our understanding of the EBL by measuring the spectral energy distribution of extragalactic sources, including active galactic nuclei, starburst galaxies, and galaxy clusters. 37. X-ray emission from galaxy groups. Galaxy groups are smaller assemblies of galaxies than clusters, consisting of a few dozen to a few hundred galaxies bound together by gravity. These groups contain hot, X-ray emitting gas confined within their potential wells, as well as individual galaxies undergoing interactions such as mergers and tidal stripping. Chandra's observations of galaxy groups reveal the presence of X-ray emitting gas associated with processes such as galaxy mergers, stellar feedback, and gas accretion. By studying the properties of X-ray emitting gas, such as temperature, density, and metallicity, astronomers can investigate the dynamical states and evolutionary histories of galaxy groups, as well as the connections between galaxy groups and larger-scale structures such as galaxy clusters and filaments. 38. X-ray reflection nebulae. X-ray reflection nebulae are luminous structures surrounding young stellar objects, illuminated by X-rays from nearby sources such as accreting black holes or hot plasma. These nebulae consist of gas and dust that scatter and fluoresce in response to X-ray radiation, producing characteristic features such as reflection halos and fluorescent lines. Chandra's detection of X-ray reflection nebulae provides insights into the interaction between stellar radiation and surrounding material, including dust grains, molecular clouds, and protoplanetary disks. Studying the properties of reflection nebulae, astronomers can investigate the composition, geometry, and dynamics of the surrounding environment, as well as the processes of star formation and planet formation in stellar nurseries. 39. X-ray emitting galaxy halos. X-ray emitting galaxy halos are extended regions of hot gas surrounding galaxies, extending far beyond their visible boundaries. These halos contain hot, X-ray emitting gas enriched with metals synthesized in stars and supernovae, as well as cosmic rays and magnetic fields. Chandra's studies of galaxy halos reveal the complex interplay between stellar feedback, gas dynamics, and the gravitational potential of galaxies. Measuring the properties of X-ray emitting gas, such as temperature, density, and metallicity, astronomers can investigate the processes of gas accretion, galactic outflows, and chemical enrichment in galaxy halos, as well as their role in the formation and evolution of galaxies and their surrounding environments. 40. X-ray absorption by intergalactic gas. X-ray absorption by intergalactic gas is a phenomenon observed in the spectra of background sources such as quasars and active galactic nuclei, where X-ray photons are absorbed by intervening gas clouds along the line of sight. This absorption produces characteristic absorption lines in the X-ray spectrum, which can be used to probe the properties of the intervening gas, including its density, temperature, and metallicity. Chandra's observations of X-ray absorption by intergalactic gas provide insights into the warm-hot intergalactic medium, WHIM, a reservoir of baryonic matter linking galaxies across cosmic distances. Conclusion: the Chandra X-ray Observatory continues to illuminate the mysteries of the universe, unveiling the hidden workings of cosmic phenomena across a vast range of scales and environments. With each observation, Chandra expands our understanding of the high-energy universe, revealing the intricate interplay between celestial objects, matter, and energy. From the feeding habits of supermassive black holes to the birth of stars and galaxies, Chandra's legacy of exploration and discovery inspires awe and wonder, propelling humanity toward new frontiers of knowledge and understanding. As we delve deeper into the cosmos, Chandra's keen eye and insatiable curiosity continue to reveal the beauty and complexity of the universe, inviting us to explore and contemplate the wonders of the cosmos. If you enjoyed from this video, please don't forget to like and subscribe our channel for future interesting videos. Thanks for watching.